Thanks, Andreas. So I'm Kshiti, and I'll be talking about this work I did with Ignacio Sirac and Alvaro Alhambra for my master's thesis at MPQ. So I'll start with the motivation. So, in general, it is widely known that entanglement is really interesting for understanding many physical properties of many body systems. And in particular, as we have also seen in the conference, it's like very useful for many computational understandings and also for condensed matter physics. And so, in general, when we talk about ground states, there's like if you see some kind of area law scaling in the certain entanglement measures, it usually implies a presence of low entanglement, and it also signifies presence of like localized correlations in the state, and and finally like classical efficient classical approximations in terms of tensor network states. And on the other hand, if you are on the high entangled side, when the states are highly entangled, it usually implies presence of quantum phase transitions and some kind of critical behavior. And in this case, usually the classical methods don't perform well. And so in this work, we actually investigate the spectrum beyond the ground state. So we try to relate this like behavior of entanglement in explaining physical properties beyond the ground state. And this is also related to recent quantum algorithms proposed for simulating systems at finite temperature. So these were quantum algorithms, but we'll be looking at classical methods. And so, broadly, I would like to answer or address these two questions, which are that through the study of entanglement in this finite energy density sector, what can we decipher about the system? So, what kind of physical properties we can understand? And this, secondly, like if we can still find non trivial tensor network approximations, like we are able to do in the case of ground states, whether we can also do this in the bulk of the spectrum. So now I'll talk about some properties in the bulk of the spectrum. So as you can see in the figure, by the bulk, I mean like states a bit far from the ground state. And so generically, these eigenstates of local Hamiltonians in like far from the ground state have volume law scaling of entanglement. And this means that okay, this was shown by Page in 1993. And also from thermalization studies, it is known that these eigenstates with finite energy density approximate thermal behavior. And this also relates to the eigenstate thermalization hypothesis, which says that these states capture the local properties of a system in thermal equilibrium. And more generally, there is a statement called canonical universality, which states that also some states with sufficiently small energy fluctuations can approximate thermal behavior. So, not just single eigenstates, but also a width around these average energies. So, again, I ask the same question, which is it still possible to classically simulate pure quantum states with finite energy density? And now we have this extra information that usually these states are very entangled, so we don't expect to exactly approximate the eigenstates. But still, can we address this major bottleneck, which is entanglement in bulk of the spectrum, somehow? And this is what we'll try to do next. So, for approximating low variance states, first I would like to introduce a correspondence between entanglement and variance of the spectrum energy spectrum distribution of this state psi, which is a pure state. So I have drawn this line, and there are two extremes to this line. One is the product state, and the other one is the eigenstate. The product state has a high variance and a very low entanglement. And on the other side, the eigenstate has no variance because it's just one term in this expansion. And but we saw that it has a very high entanglement. But we don't know much about the things in the middle, the states in the middle, and so, what we would like to do is find the best of both worlds, which is low variance and low entanglement. So, if we somehow have low variance, we are able to go to this idea of eigenstate thermalization and canonical universality and hope to approximate thermal behavior if we find such states. And if it has low entanglement, we can also classically approximate. So for this, we go to this middle region and try to find tensor network approximations for these states. Okay, so for this, I need to introduce a tool which we use, and it's a simple operator, which is power of the cosine function of the Hamiltonian. And this filter has this control parameter m, and it is applied to a high variance product state with energy E. So, okay, so there are two limits of this filter. So, if you don't apply it, like if you take m equals to 0, it's just the identity operator, and then we stay at the product state. On the other hand, if m is very large, this becomes like a delta function, and then we are able to just single out this eigenstate at energy E. Okay, so now, so these are the two limits, and we want to somehow locate this barrier in the middle, which tells us that, okay, right side of the barrier will be states we will be able to approximate classically, and on the left, we won't be able to because it gets more and more entangled as you go to the left. So now we'll try to approximate this barrier. Okay, so for this, we introduce this we want to find this classical algorithm to apply the cosine filter to a product state. And this is like the state, the filtered state. And this is the cosine operator and the product state. For this, to prepare the state, we use two tools, which is the first one is the Berry-Esseen theorem for quantum lattice systems. And the second one is the MPO approximation of the cosine filter. So first, I'll try to explain the Berry-Esseen theorem and then specialize it for the quantum case. So this formal statement, the original statement of the Berry-Esseen theorem is that if you have n independent random variables with the same mean and variance, then the cumulative distribution of the sample mean, which is this, and the standard normal distribution converge. Um, so these are the cumulative distributions of these two things, the sample mean and the Gaussian. And we take the maximum over all the energies, for example, and see that it is actually bounded as 1 over square root of n. So in the limit n tending to infinity, the two distributions converge. And this quantifies how close this distribution is to the Gaussian. And here we can see that, for example, this is just an example of like in the case where we are near x equals to 2, the difference attains the maximum, and this maximum would be bounded by 1 over square root of n. And so the original statement was actually studied a lot by Berry and Esseen, and they were trying to quantify the rate of convergence. So like the constant here, which we just wrote the scaling, but they were looking at the constants, and there were many people who actually improved the constants constant like after Berry Esseen also. And but we only care about the scaling. Okay, so now I'll introduce the quantum Berry-Esseen theorem, and this is like the slide with the notation. So we take a state with finite correlation length and variance sigma. So this is the state. And then we take the cumulative energy distribution of the state, which looks like this, and the Gaussian cumulative distribution with the same average E and variance sigma square. So it has the same energy and variance as this original state. And then the Berry-Esseen error, I'll call this Berry-Esseen error, is defined as this, where this zeta n is this Berry-Esseen error. And this quantifies the maximum distance between these two distributions, the cumulative distribution. And for, the classical Berry-Esseen theorem was this scaling. And now for the quantum Berry-Esseen theorem, it was already shown by Brandau and Kramer, and they actually submitted it to QIP 2015. And the scaling was this, with this logarithm n to the power 2d factor. This d is dependent on the lattice dimension. And this was for finite correlation and states. We specialize it for product states and provide a very different proof. Actually, it's very short proof. And we are able to get rid of this polylog factor in the numerator. And this actually is really crucial for what kind of variance bounds we get later. So also we are able to get rid of the dependence on the lattice dimension. So this will be used to approximate the discrete probability distribution, which is like the state has this distribution on the eigenenergies, which is discrete, and we'll approximate with a continuous Gaussian. Okay, so I'll give a brief outline of how we get this 1 over square root n scaling for the Bayesian error. So we take this characteristic function of energy for a product state, and from Essein's inequality, it is known that this Bayesian error is actually bounded by this difference between the characteristic function and the Gaussian. And then for short times, it was shown in this work by Wilden Alhambra from 2023 that this characteristic function is actually very close to the Gaussian, and this is the upper bound. And then with the right choice of parameters, it can be shown that this Bayesian error is bounded like this. So note this is for product states. Okay, no, so now we need to go to the second part of the tools, which is MPO approximation of the cosine filter. Okay, so I would like to bring your attention to this very simple binomial expansion of the cosine filter. And then we see that this has this this representation in terms of unitaries, time evolution operators. And it is known that these time evolution operators can be expressed as an MPO with this bond dimension. This is the MPO. And the bond dimension depends on the, it's exponential in the time. And so here in the edge, like the last terms, like the values of small m, which are very large, this time is large. And then we might get very large bond dimensions, but then we notice this Chernoff bound on binomial coefficients, through which we are able to actually get rid of the tails and truncate the sum to just square root of m terms. And this is like the MPO approximation of the cosine filter, which I call GY. So now the bond dimension will be polynomial. So far, I have explained this much, which is we have the product state, we apply the MPO approximation, and then we get this filtered state MPS. And now, so here, this is the product state, and we get this filtered state. Now, I would like to apply the Berry-Esseen theorem to find a variance bound for this filtered state. Okay. So for the variance calculation, there are some limiting factors. Of course, one of the limiting factors is this scaling, because it kind of restricts the size of. Okay, first we need to divide this energy axis into small bins of size lambda, and these bins are then each approximated with the continuous Gaussian distribution. And if we take the bin size to be very small, then the Berry-Esseen error accumulates. You have to add the Berry-Esseen error for the number of bins, the total number of bins. And then there's this trade-off, and we need to restrict the size of the bin to some finite value. And from this, we see that if the actual scaling was the original, the first one, the variance bound would have been this, but because of this improvement, we are able to go to order 1 variance, which is independent of the size of the system. Okay, so now I'd like to highlight the second main result, which is that the bond dimension is bounded like this. So to understand this expression, I'll just take some examples, specific ones. So for variance 0, as expected, the bond dimension will be exponential. It will be very large. For the product state, it will be 1, but this is an upper bound, so it will be some constant here. And then in the middle, we see that if we substitute this order 1 in this delta, we get a polynomial bond dimension. So this is the smallest variance that can be achieved. And anything right to the right side to this barrier will be approximable using this cosine filter. Okay. Okay, so now this is like good so far, and we would like to see if we can further improve this result. And for this, we specialize to the case of ETH Hamiltonians. And ETH, as I also mentioned before, is the hypothesis that states that in isolated quantum systems, the eigenstates behave like thermal ensembles. And eigenstates formed the thermal ensemble, and this was proposed by Strednicki in 1994. And so it was also shown by Wilming et al. In 2019 that these individual populations are exponentially small. So, like the states of obeying ETH have this individual population which is exponentially decaying in the size of the system. So, if we assume this, we can conjecture that if we specialize to ETH Hamiltonians, we can get a further exponential improvement in this numerator, and this means uh, that the distribution will converge even faster to the Gaussian distribution. So if we now take this new ETH conjecture, then we can see that we first had this variance, then we improved it to this, and for this last conjectured scaling, we get this 1 over log n. So we are able to move this barrier even to the left, which is good. And that means that we can approximate even more low variances. And this time it's also tending to 0 in the thermodynamic limit. Okay. So now I would like to summarize briefly. So there's this, we showed that there's this tensor network algorithm to prepare low variance quantum states. And so this is the red barrier. We have highly entangled states which we cannot approximate on the left, but there are many non-trivial states on the right which we are able to approximate, and we hope to also approximate some kind of thermal behavior with the states on the right of this barrier. And the tools we use is this based on Gaussian approximation, which is a consequence of the Berry-Essien theorem. But I would like to mention here that we are looking for applications for the Berry-Essien theorem. And if any one of you has any ideas, you can contact me and we can discuss more. And the second thing we used is this MPO simulation of the cosine filter, which was based on matrix product approximations of this cosine filter, which was based on this approximation of the matrix exponentials. So there's a result by Demaski and Liu from 2019, which says that the states with variance 1 over log square n can achieve thermal observable values. So states even smaller than this. So from our result, it seems that we cannot reach this variance. But since we consider worst case bounds, in actually we consider the worst cases where it might not go to the smaller variances. But you see, this is like order 1 over log n. So in practice, it is possible to go even to smaller variances, which is also shown in this classical numerical result by Banuls et al. In 2020, where they are able to get 1 over log square n. Okay, so this was what we did, but now I would like to give an overview on what the research directions could be in the next few years. So this cosine filter algorithm was actually proposed as a quantum algorithm, and these were the theoretical proposals. And then there was an experiment also performed on Quantinuum's ion trap device. However, since then, there have been multiple fully classical proposals, and they have been implemented through tensor network approaches by these papers. So here, our work stands here is that like we aim to rigorously justify the performance of these classical algorithms for measuring thermal values. So we show that this is like the benchmark which quantum future quantum algorithms have to surpass to provide even better variances, smaller variances. And so the filtering approaches are potentially applicable on near term devices, which was shown on this small device by these people. And but now we would like to ask the question that in which cases can they yield thermal expectation values beyond classical reach? So yeah, thanks for your attention. And yeah.
Thank you very much. Are there any questions? If so, please come to the middle as usual.
Yeah, I don't know if this makes a connection to the Anurag Anshu's tutorial or not, but there was this question of like epsilon error
Mhm.
states
Yeah.
and epsilon energy states.
Yeah.
Can you comment like if there is any connection with your
Yeah.
work to that?
Okay.
Yeah.
So the thing is that we are assuming ETH everywhere, and this limit of ETH is usually in the finite energy density regime. But the discussion about this epsilon energy states is really close to the ground state. So yeah, I'm not sure if there's a connection there. Yeah.
Um, Very nice results. I was wondering, it seems like the fact that you're able to achieve this crucially relies on the fact that it's 1D.
Um,
Is that true? And do you think that in higher dimension can you get like finite variance, like sublinear variance,
yeah.
and quasi eigenstates in the middle of the spectrum?
Yeah. Okay. So the Berry-Essien result is actually valid in any dimension. So we can actually apply it in higher dimensions as well. But the limiting factor here is this MPO approximation. So I showed two tools we use. The second one, which is MPO approximation of the cosine filter. This we are not sure yet whether we can find a PEPO, like projected entangled pair operator approximation in the two dimensions. So that is still like underway because yeah, that requires rigorous tensor network theory results. And yeah, so this we are not sure whether we can achieve smaller variances in the higher dimensions.
Thank you for this nice talk. Maybe a bit of a naive question, but for ETH Hamiltonians, you show this exponential decay of
Yeah.
the. Does the reverse also hold? Like, if you could show the exponential decay, then this implies sort of ETH for.
The reverse, that if there's in the Berry-Essien error, if there's exponential decay, could be, yes. I think that that direction makes more sense to me. Yes. Yeah. But I need to think about this.
Thanks for a nice talk. I think we can create a thermoperiodic quantum state by applying exponential to the minus beta h given the inverse temperature beta. Could you comment on comparison to the case?
Yes, so the thermal pure quantum states, as far as I know, are highly entangled. So these are these states which um, have variances scaling as 1 over n or even smaller, 1 over n square. And we actually just go until 1 over log n. So there's this, there's difference in the entanglement because we want to approximate classically. But the good thing still is that we are still able to see thermal behavior being recovered by these states. So if yeah, but thermal pure quantum states are even stronger, like they have even smaller variances.
Thank you.
No worries.
Any last questions? Please come to the middle.
Hey, thanks for the nice talk. I had a question. So the cosine filter is not generally unitary, so it'd be hard to.
Yeah.
So if you have a high variance and you apply the filter,
Yes.
then do you have a probability of success? Do you have any idea of like how to make it unitary
yeah.
or
So
closer to?
yeah. So the thing I think is that So the limiting factor even in our results was the norm of the state, which is this thing here, this thing. So this is the main thing which limits the smallest variance we can reach. And that I think will also be true in when you try to approximate it with a unitary. So yeah, I don't know if that answers the question.
Yeah, I mean, classically, you could just normalize the matrix product state, but it's hard to do that on a quantum. Right.
Yeah, but then it will appear in the minimum variance that you can achieve, right? So in our case, the limiting, so the norm also plays a role in our case, and the minimum variance which we can reach is limited by the norm.
Okay, thank you.
Great. So any other questions you have to ask after the end of the session? So for now, let's thank the speaker again.
Thank you.